You have already learned that if there is no change in the state of a body, its temperature increases when it absorbs heat energy from the surroundings and decreases when it emits heat energy. Now let us study the factors that influence the heat required to change the temperature of a body. Consider a given quantity of water being heated using a source that supplies heat at the rate of 100 joules per second. If the initial temperature of water is 303 Kelvin and the temperature is increased to 308 Kelvin at the end of 3.5 minutes and to 313 Kelvin at the end of 7 minutes, the amount of heat absorbed for a rise in temperature of 10 Kelvin is double the amount of heat absorbed for a rise in temperature of 5 Kelvin. This means the quantity of heat absorbed or emitted, delta Q, by a body is directly proportional to its change in temperature, delta T. Let this be equation 1. Heat capacity denoted by S of a body is defined as the heat absorbed or emitted per unit change in its temperature. Therefore, S is equal to delta Q by delta T. The SI unit of heat capacity is joules per Kelvin. In the experiment shown earlier, heat absorbed by the given quantity of water in 7 minutes can be expressed as delta Q equals to RT. Substituting the values of R and T, we get delta Q equals to 42,000 joules. The corresponding rise in temperature, delta T, is 10 Kelvin. Substituting the values of delta Q and delta T, the value of heat capacity S is 4,200 joules per Kelvin. Now let us double the quantity of water. Then the time required to raise the temperature from 303 Kelvin to 308 Kelvin is 7 minutes. This means when the mass of water is doubled, the heat required to raise the temperature by 5 Kelvin is also doubled. Hence, the quantity of heat, delta Q, required to raise the temperature of a body depends on its mass also. Therefore, delta Q is directly proportional to mass m. Let this be equation 2. From equations 1 and 2, we can write that delta Q is directly proportional to m delta T, or delta Q is equal to S m delta T, where S is the specific heat capacity of the substance. Specific heat capacity is the quantity of heat absorbed or emitted by a unit mass of a substance for a change in its temperature by 1 unit. Specific heat capacity S can be expressed as S equals to 1 by m into delta Q by delta T. The SI unit of specific heat capacity is joule per kilogram Kelvin. Specific heat capacity depends on the nature of the substance. Different materials have different specific heat capacity values as shown in the table. The specific heat capacity of water is 4,186 joules per kilogram Kelvin. For practical purposes, we can take the value to be 4200 joules per kilogram Kelvin. Water is used as a coolant in automobile radiators because of its very high specific heat capacity. The specific heat capacity of a substance also depends on its temperature. Different amounts of heat are required for a unit rise in temperature of a unit mass of a substance at different temperatures. For example, the variation of the specific heat capacity of water with temperature is as shown. This is why a specific temperature range is given in the definition of calorie, which is a general unit of heat. A calorie is defined as the amount of heat required to raise the temperature of 1 gram of water from 14.5 degrees centigrade to 15.5 degrees centigrade. Sometimes, it is more convenient to describe the quantity of a substance in terms of moles, mu, rather than mass, m. When a given substance is expressed in moles, its specific heat capacity is known as molar specific heat capacity and is represented by C. The molar specific heat capacity of a substance is defined as heat capacity per mole of the substance. This is given by C equals to S by mu equals to 1 by mu into delta Q by delta T. The SI unit of molecular specific heat capacity, C, is joules per mole Kelvin. Molar specific heat capacity also depends on the nature and temperature of the substance. The definition of specific heat capacity is applicable for all states of matter, namely solids, liquids, and gases. But for gases, the heat required to raise the temperature depends on the process involved. If we heat a gas by keeping its pressure constant, then the heat delta Q required to raise the temperature of 1 mole of gas by 1 unit is called its molar specific heat capacity at constant pressure and is denoted by Cp. Cp is equal to 1 by mu into delta Q by delta T at constant pressure. The molar specific heat capacity at constant volume, denoted by Cv, is the heat required to raise the temperature of 1 mole of a given gas at a constant volume by 1 unit. Cv is equal to 1 by mu into delta Q by delta T at a constant volume.